In this video, we're going to continue with the potential energy diagrams and collision theory. We're going to try to do some examples where we label some potential energy diagrams and also where we just go over the difference again between endothermic and exothermic energy level diagrams. So let's take a look at these two diagrams here. Here we have an example of an endothermic one and an exothermic one. So just to clarify, when we're looking at the endothermic one, your reactants and products is the first thing you want to look at. You want to see where they are relative to each other. In endothermic reactions, you want to see that your products are higher in energy than your reactants because there was an absorption of energy. Energy went in overall. And so your delta H would be higher than zero. It would be positive, in other words. And that's endothermic. Once again, you have your potential energy diagram, your potential energy on the y-axis, and your reaction progress on the x-axis, heading from left to right. So your delta H would really be the difference in energy between the reactants and the products. And then your activated, your transition state or activated complex is essentially the peak of the curve there. Your activation energy is from your reactants all the way up to that peak of the curve. So that's the activation energy for this endothermic reaction over here. Now, if we take a look at the exothermic reaction, we have the reactants over here and the products over here. You know it's exothermic because the products are lower in energy than the reactants since there was a release in energy. And that leads to a delta H that is smaller than zero. In other words, that is negative. Your activated complex occurs at your transition state, which is the highest point in the curve there. It's the most unstable because your reactants are transitioning to become products. And then the EA would be from where your reactants are all the way up to the highest point. So right there, that's the EA. Now, keep in mind, here we're looking at the EA forward because I'm talking about going from left to right. But if you want the EA reverse for this reaction, you would essentially have to look at from here all the way up to the highest point. So that would be EA reverse specifically. So this over here is your delta H being less than zero. Remember, delta H is, regardless of what type of graph you're looking at, they do not include the EAs. So they do not include EAs. So let's go ahead and take a look at a labeling problem where we have two different reactions and we have to label what the different components are. If you want, you can pause the video and try it out yourself to see if you understand the concepts, and then you can check your work after you're done labeling. So we want to label the type of thermochemical reaction, meaning is it endo or exo? So my first thing that I'm going to do is I'm going to label the reactants and products actually. So I know on the left side we have the reactants, and on the right side, we have the products. I'm going to take a look at how they differ in terms of energy. So my products are lower in energy than my reactants are. That means energy must have been released overall. Since energy was released overall, this one here is an example of an exothermic reaction because energy was released. If you want to label your delta H, it's simply the difference in energy between the reactants and products. So this would be over here, our delta H. Just gonna move it here, delta H, which is less than zero, which makes our reaction exothermic. We then have to label the transition state along with the activation complex and also the EA reverse and EA forward. So transition state is right over here, transition state, and that's where the activated complex would form. So you'll have a transition state with activated complex, AC I'll call it, okay? And the EA is from reactants all the way up to the highest point. So this is the EA over here that's required. Okay, so there's our EA. And that's our EA forward because we're going from left to right. Now, if you wanted to, you could find the EA reverse. And so the EA reverse, if you were going from right to left this way, would be from your, essentially what were your products, all the way up to the highest point. So that would be from here all the way up to there. And this would be your EA reverse. And remember that if you want to find the value of your delta H, you could simply do, remember delta H is equal to EA forward, EA forward, minus EA reverse. And we'll do some more specific examples with actual numbers later. But right now it's about being able to label the graph and putting all the appropriate spots in the appropriate areas there. So that was an example of an exothermic graph. Let's take a look at the next one to see if it's endothermic or exothermic again. So same thing here. You can pause the video and try to label yourself first, and then afterwards unpause and see if you're on the right track. So once again, my first step is going to be to label reactants and products right there. I notice the products are higher in energy than my reactants. Therefore, there must have been an absorption of energy. So this is an endothermic system. The delta H is simply the difference between reactants and products. So delta H is over here, and it is positive. It's greater than 0. To find your EA, you basically find the highest point. That's your transition state with the activation complex. The EA forward, going from left to right, is the reactant up to the highest point. So this is the EA forward. And if I want to find my EA reverse, going from essentially right to left, I'm doing my what were the products, my new reactants up until the highest point. So this red part only, not the blue part, the red part only is my EA reverse. And remember, just like in the previous example, if you did EA forward minus EA reverse, you would get your delta H again. So first step is, can you label a potential energy level diagram? Can you identify if you're dealing with an endothermic and exothermic, and explain why? Can you find the EA forward? Can you find the EA reverse? Can you label that transition state with the activated complex? And if you can do that, then you're ready to do the next example where you have specific numbers given to you, and you have to draw your own energy level diagrams with the proper labels and also with the proper numbers. So that's what we'll do in the next video. For now, just make sure you can label and properly draw at least the skeleton for a potential energy diagram. Can you sketch endo versus exo and show the differences?